Okay, everyone, let's get started. So we've now gone over the introduction and how we're going to run the class and the course mechanics. I wanted to now give you a preview of all the topics that we're covering in the class. Okay, so these set of slides are available to you there in Canvas under Handouts 2023. So the one we're doing is Notes 1 Introduction. And we'll see how much of it we can get through, okay? So I think you already know my name, how to contact me, and this class is it's about modern communication systems, and the aim is we're going to explore fundamental aspects of modern communication systems, and as I mentioned to you earlier, there's a strong foundation. So the reason that modern communication systems have been so successful is that there's a strong foundation in theoretical ideas, specifically from information theory. And information theory is about the fundamental limits of communication. So what do we mean by fundamental limits of communication? What we mean is things like, what's the maximum rate of reliable communication? So for example, I have my phone here and I'm trying to stream high definition video. Can I do it? At what resolution? Maybe you can stream low resolution video, but not high resolution video. So the rate of communication or the rate of communication that the system is able to support will determine what resolution you can stream, right? So information theory is about what are those limits? Okay, and so information theory was developed by Claude Shannon in 1948 when he wrote a monograph called A Mathematical Theory of Communication. And what this paper did was it built a framework, which later we call information theory, which essentially looked at the limits of reliable communication. All right. And the reliable here means, well, that the receiver can actually decode the information. Right. Now, after Shannon, what people did was, so this changed the way that people thought about communication system design. Prior to Shannon, communication systems existed, but people would just build it, make it work, sell it, and just be done with it. They didn't know if it was good or bad. After Shannon said, here's the best you can do. Right? Well, now if I build a system and it's very far from the best, there's opportunity for me to make it better. And people engineers have spent the last 70 years from 1950 to now building better systems, right? That's why, for example, we say that deep space communication, Wi-Fi, your mobile phone are all directly driven by what Shannon envisioned, right? Shannon is not the one who designed the phone, but he set the fundamental limit that made people want to design better communication strategies for phones. Okay, and from the 1970s onwards, we started to see them being rolled out in implementation. So what we're going to talk about in this class are some of these strategies, okay, that allow you to build better, more efficient, robust communication systems. All right. So communication is fundamentally about information. And this was actually Shannon's insight. Shannon's insight was that it's not really about communication. It's not really about what you want to communicate, right? I mean, normally communication is about semantics. By semantics, what we mean is meaning. What's the meaning of things? Shannon was a little bit more clinical. He said, remove meaning. I don't care about meaning. He defined a new notion of information content, right? That we now represent in terms of bits, right? He said, take meaning out of it and just what is this new information that he defined, and said, okay, how can we communicate that, right? He left the meaning, the semantics to the human, right? So for example, if I say something to you, it might move you, it might generate emotion in you. Shannon didn't care about that. He says the phrase, I love you. Okay, I'll just take that as a set of words. I'll turn it into bits and I'll transmit it. Whatever happens, whatever the human does with it is up to the human. The communication system only cares about sending the words, I love you. Okay, and so communication is fundamentally and is based about information. And so when we talk about communication systems, we need to talk about information representation. Maybe I try to see if I can. Okay, so communication. Okay, is about information representation. All right, and typically when we are representing information in these signals, we broadly talk about analog versus digital signals. I think this should be kind of familiar to all of you, right? Analog and digital, right? I mean, most engineering systems have analog to digital converters, right? A to D converters. So I want to put forth the idea that information representation is a starting point for communications. The information that you have, how are you going to represent it in the signal? Okay. Now keep in mind that analog versus digital is a little bit tricky, because you could argue our world is analog. Okay. So I'll tell you what digital is in a second, but digital is actually fiction. It's in our imagination. Our world is analog. So when you receive something, it's an analog signal. When you transmit something, it's an analog signal. There's no ways about it. You don't transmit ones and zeros. You transmit analog signals. What is different in analog and digital system is how information is represented. Okay, so when you have an analog signal is a signal which takes on a continuous set of values over continuous time. So you can think of there being two dimensions, time axis and value axis, right? Like you have, think of a musical song. It exists in time and it has certain values, the sound. So there's a time axis and a value axis. When both are continuous, we have an analog signal. Okay, when you sample time, now to go to digital, it's a two-step process. You need to discretize both the time axis and the value axis. So when you discretize the time axis, you get a discrete time signal. That's sampling in time. Okay, so you sample in time, step one. Step two is you discretize in value. That is called quantization. Okay, so a discrete time signal is a sampled analog signal, sampled in time. A digital signal is a discrete time signal, which is quantized in value. So here are the examples of that. So the diagram on the left here is an analog signal, and it takes continuous values in time. So it's continuous over all time as well as in value. Okay, so in this case, I've drawn a triangle. It exists for all the time between, let's say this was 2, okay, and this is 0, right? So it exists between 0 and 2, and it takes all possible values between 0 and 2 for all time instances between 0 and 2. This is an analog signal. When we sample the signal in time, then we sample it. Hang on, I'm going to make this a little bit finer. When we sample this signal, okay, in time, oops. Okay, then it exists only at these time instance. That one. Okay, so we save the value only at these instances. But what value do we store? We store the actual value of the signal. Okay, because we are not changing the value just yet. Okay, it's the same value, but we only store it at a specific time. So this is a discrete time signal. Now, what we're going to do is we're going to now discretize the value axis. So we still have a time instance, but we take the y-axis now and chop it up. And so instead of being any value between 0 and 2, so remember this was 0, and this was 2, and that was 1, right? Between any value between 0 and 2, which is the way it was before, we now create these intervals, these bins, and say that, oh, I'm going to just remember which bin it fell in. So, for example, all these values here are in the same bin. So they'll be represented by the same value. Okay? And the same thing, whatever is in this bin will be represented by one value. That will depend, the value that you represent, the quantized value, depends on the quantizer. But a good way is to choose the midpoint, right? So for example, I might represent everything in this bin maybe by this midpoint, right? So that's a midpoint quantizer. So what have we done? We've now sampled in time. You see the time instance here, and we sampled in value or quantized in value. When we do that, we get a digital signal. So everybody good on that? Do we understand what's a analog to discrete time to digital? Okay. Now keep in mind, this is all about information representation. Later we'll see that these values here, because they come from a discrete set, they be represented by bits. So if I in this case I have 1, 2, 3, 4 levels, right? So how many bits do I need to represent 4 levels? 2 bits, right? Yeah, so now all these values are represented by 2 bits. And I can store those bits. If I want to communicate those bits, I need to do modulation onto an analog signal. But it's still a digital signal because the information is represented digitally. I might still transmit an analog signal, but the information inside there is digital. So that's like, often this is glossed over when people talk about signals and systems and communication systems. It's all about information representation. How are you representing the information? Okay, so in summary, a discrete time signal is a sampled in time analog signal. And some examples of that are pulse amplitude modulation, pulse duration modulation, pulse position modulation. Don't worry too much. I'm just giving you some examples. We'll go into details on this later. But the idea here is that the information here is stored in either the amplitude, position, duration, or position. Okay? All I'm doing is sampling in time. Once I quantize in value, we get a digital signal. Okay, and examples of that are PCM, pulse code modulation, and delta modulation. In this class, we'll talk about PCM. Okay, and we'll see that PCM is the bridge from analog to digital. All right? Okay, so here's some examples. On the top, we have this is the analog signal. Okay, this is the original analog signal. It's a sine wave. You can see it exists for all time or continuous time. You can take any value, but any value between this one and that one, right? But it can take any value. It's not restricted. Okay, no. So what we're going to do with this signal is first we're going to sample it in time. We're going to sample it at these time instants here, and so on. Okay, where you see the dotted lines. So I'm sampling in time. Now, I could be done. I could just store that value. But if I want to communicate this, you can't just send values. That's not how communication works. I need a signal to transmit. So here I'm giving you an example of a signal. I'm going to send a pulse. That pulse is going to have the height that corresponds to the height at where I sampled it. When you do that, we call it pulse amplitude modulation. All right? If instead of the height of the pulse, I send a pulse of varying width, and this width here depends on the value of the sine wave, we call it pulse duration modulation. Again, just giving you some examples. If I now quantize value as well, right? So remember when in the other example when we had 4 values, I had 2 bits. Suppose in this instance I turn this into, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose I have 1024 levels. Then I can represent each level by 10 bits. So here are those 10 bits. Suppose that this height here falls into the bin that's represented by this 10-bit pattern, right? So now I've converted this value to these ones and zeros. Of course, if I want to store that on a computer, I just store it. But again, if I want to transmit it, I need to generate a waveform. And so here I'm going to generate pulses. I'm going to use on-off keying to say when there's a 0 here, I don't send a pulse. When there's a 1 here, I send a pulse. Okay, and when we do that, we call this PCM, pulse code modulation. And pulse code modulation is one of the most popular ways of transmitting a digital signal. Now keep in mind that, so in this class, the word, we're going to talk about modulation, but this is not the modulation. This modulation is to generate a waveform that you can transmit. Now, typically, we don't transmit these kind of waveforms. We're going to take this waveform and we're going to move it to a carrier frequency. That is typically what we mean when we talk about modulation in communication systems. This is what's called baseband signaling. This is at 0 frequency, okay? Meaning the center frequency of my modulator is 0. But this is still called modulation because it takes bits, ones and zeros, and it generates a waveform that you could transmit. Let's talk a little bit about analog versus digital. Why do we use digital signals, right? What's the benefit of digital over analog? Well, there are a couple of benefits, and I'm listing them here. So digital signals are less sensitive to noise. The way to see it is go back here, okay? If you go and focus your attention here, okay? If I transmit this waveform at the receiver, I want to recover that bit pattern, right? Once I get the bit pattern, I can figure out which level it was, and I can find out the value. And I can reconstruct if it was a music signal, I can reconstruct it, right? So what decision do I have to make here? Your goal is to recover that, right? So how did we generate it? We use on-off keying. If there's a 0, no pulse. If there's a 1, there's a pulse. So at the receiver, you get this noisy signal. What are you going to have to do? All you have to do is decide, in this part, is there a pulse or no pulse? No. In this one, is there a pulse or no pulse? You know, in this interval right here, is there a pulse or no pulse? So this is my symbol, but this is my sub symbol. So in my sub symbol interval is or no pulse. And that's the decision the receiver has to make, right? Now, I want you to contrast that with the decision that the receiver has to make here. How am I going to recover that? So if I give you, so here the information is encoded in the height. So suppose the pulse gets distorted. Can you figure out what the original height was? No, right? It's very hard. So if I convince you that, so this is discrete time, so don't worry about time, but it's analog in value. It's very hard. It's not robust to noise at all, because you don't know if the noise, is it noise or is it the original signal? But if you go down here, the only decision I have to make is pulse or no pulse. That's much more robust. Of course, you can still make an error. So do you get why? This is to justify why I'm saying digital signals are less sensitive to noise. Because for the same noise, the decision I have to make is easier. Right? You can imagine that it's easier for you. Okay, like I could say this. Okay, I'm going to make a sound or not make a sound. All you have to do is decide, did I make a sound or not? Is that easier than saying, I'm going to speak and you tell me what level I spoke at? Which one is easier? The first one. Right? That's why digital signaling is more robust than noise. And that's why we use it. Like, if you don't understand anything, understand that. That is why digital systems are king because of they're more robust than noise. Okay. Then a few other things. You can repeat digital signals because you can get rid of noise. You can repeat it. You can decode it and repeat it. With an analog signal, you cannot. You will just have to, when you repeat it or amplify it, you will just amplify noise. Okay, so you typically, for analog signal, you don't want to repeat because you're just amplifying noise. Digital signals are easier to manipulate. I'll say something about that later. In most cases, the hardware and circuitry is easier for a digital signal. And to me, this is the manipulating part. The most important part, again, this is a repetition of some of the other points, but it's still worth repeating. Digital signals are more robust and more efficient. You can do things like multiplexing, sharing of resources, but the two things we're going to study in this class that you can do with digital signals is source coding and channel coding. Source coding is data coding. Channel coding is things like error detection and error correction. And frankly, it's magic. It's like saying an error happened, and without you knowing what the error is, you can correct it. Huh? It's error correction. I'm not sure what self-correcting means, but yeah. So and this strategy of channel coding allows you to do that. And where does Shannon fit into this? What Shannon did was he proved a theorem that says that under certain conditions, good channel codes exist that allow you to do all this stuff, right? Like prior to Shannon, people didn't know, but he said under these conditions, good channel codes exist. It turns out those conditions match our real world, so good channel codes should exist, and so people went hunting for them. They spent the last 50 years finding them, allowing us to build very efficient communication systems. Does that close the loop for Shannon a bit? Okay. So in this class, we're going to spend, especially in the digital communications part, a lot of time on source and channel coding. Okay. So let's talk a little bit about transmitting analog and digital signals. Okay, so now we understand analog and digital. Let me ask you, what is it about? Analog and digital, if you have to fill it in, is about what? Is about information representations. That's the only difference between them. How are you representing the information? Okay, there's a lot you could say, but this is the message I want to send to you guys. Okay, so if you represent information in an analog way, you still have to generate an analog signal to transmit. And when you do that, you end up with things like amplitude modulation and frequency modulation. Okay, these are analog modulation schemes in the sense that the information is represented in an analog fashion, and then the information is embedded into the transmit signal. So in amplitude modulation, the information is encoded in the amplitude of the transmit signal. So if I'm going to send a sine wave, let's say my transmit signal is a sine wave at a certain frequency. The amplitude of that sine wave, right, is going to be where my information is captured. Right? In frequency modulation, information is encoded in the frequency of the transmit signal. So if I have a sine wave that I'm transmitting, it starts off at a certain frequency, but then the information decides the actual frequency. That's called frequency modulation. So do you see how it's analog? Because the information is directly changing some property of the transmit signal in an analog way. Now, and we're going to study AM and FM, okay? And again, right now, I'm not going to get into details. I want to give you, like I mentioned, a high-level overview. In digital, so we're still going to transmit that sine wave, but the information is digital. I've gone from analog to digital, generated these levels and ones and zeros, and now these ones and zeros are going to have an impact on the property of the transmit signal. So in phase shift keying, right? In phase shift keying, you change the phase of the sine wave. So for example, if you have 2 bits, remember I had 4 levels and 2 bits. So every sample is 2 bits. So if I'm sending a sine wave, 2 bits gives me 4 values. I have 4 phases. Maybe I shift the phase of the sine wave for 4 different ways. For example, in phase shift keying, the information is encoded in the phase of the reference signal. Okay, and there's a whole bunch of other things. You could also have information be encoded in the amplitude. So in QAM, information is encoded in both the amplitude and phase. So you can see that there's a lot of similarity to this, right? So what's the difference between this and this? What's the biggest difference between this and this? Because it looks like I'm saying the same thing. Information is encoded in the amplitude, information is encoded in the frequency, information is encoded in the phase. There's no phase here, but there could be. It turns out that there's a brother to FM called PM, which is phase modulation, and we'll study phase modulation. So the phase is not new, and this is both phase and amplitude. So what's the difference between these two? The idea of embedding the information in the transmit signal is the same. What's different is what information are you embedding? Okay, so we're going to study this. So this is when we do AM and FM, we'll study this. When we do the digital, this would be digital modulation. Communication is about information and its representation. Okay, so now let's talk about communication system block diagram. So this is the first time that we're seeing the entire communication system. Okay, and essentially this is a digital communication system, because an analog communication system only has a source and it has the modulation, the analog modulation. But digital is much more powerful. You can do things like source coding and channel coding. Okay, and so at the transmitter you have your source of information. You go through the transmitter. The transmitter has a source encoder, a channel encoder, and a modulator. Then you go through some noisy channel. There's a channel, there's some noise, and at the receiver, you're going to undo all of these. You're going to undo the demodulation, you're going to undo the channel encoding, you're going to undo the source encoding, and then eventually you push it to the sink. Now you got to wonder, what's the purpose of this stuff? Okay, so I'm going to tell you. The source encoding is data compression. And what we mean by data compression is that it removes redundant information. Now, do you believe that there's lots of redundant information or not? I'm thinking of a word. I won't tell you what word I'm thinking of. It starts with a Q. Can you guess the next letter? The English language is not infinite number of words. And if you think for a little bit, you will find that, hey, probably almost all of the words that start with Q have a U next. In fact, I can only think of one word that doesn't, and it's a country. Qatar. That's all I can think of, right? So in some sense, if I'm transmitting a word to you and I send you a Q, isn't the U redundant? If Qatar didn't exist, if 100% of English words that started with a Q had a U, would the U be redundant? I send you a Q, I should just skip the U. No, I'm trying to convince you there's redundancy in English language. And this is a simple way. It turns out there's a ton more redundancy. Now, it turns out even if it's almost all words except Qatar, it's still redundant. Because all I have to do is either skip it or send an A, right? If I skip it and the next word is not A, then previous letter was a U. So my point is, you can remove redundancy without much harm. The other thing that I often like to do is, I'm not going to do it now, but if you take words, right, and you remove every other word, you can probably understand. Or what's this thing? You can you take a word, you keep the first and last letters the same and scramble the middle. Again, you'll probably be able to make out. Why? English language is redundant. Okay, and so source coding is data compression, like WinZip. You guys zip files on your computer, right? Sometimes files go from big to small, right? What kind of files get smaller? Like text files, Microsoft Word. What doesn't get smaller? Binary files, like image, video, PDF files, binary. If they're text-based, it can compress. Binary, less compression. But my point is, there's a lot of redundancy in English, and source coding removes it. And source decoding will undo whatever the source code did, so you can understand it. Channel coding, paradoxically, adds redundancy back. It adds redundancy back so that you get robustness to noise against errors. That's what gives you error correction and error detection. Actually, you guys have figured out, in this world, there's no free lunch. You don't get something for nothing, right? You got to pay a price. The price of channel coding is a little bit of redundancy. Okay, so channel coding adds redundancy back, but it gives you robustness to noise. It allows you to do error detection and error correction. I'll show you in a minute. And the job of the modulator is to take the bits and generate a waveform that you can transmit. Right? Okay, so that's all described here, but I kind of said it in the last few minutes here. Okay, so we're going to do two examples: source coding and channel coding. Okay, so source coding. All right, so I'm going to do this. So I'm going to assume I have a alphabet of 5 letters. For example, okay, our alphabet is 26 letters. Assume I have an alphabet of 5 letters, A, B, C, D, E. And this is the frequency. Like, I have a file, and this is the frequency of occurrence of A, B, C, D, and E, okay? Now, I could design a fixed length code, meaning I want to so in source coding, I'm going to output a bunch of bits, okay? So since I have 5 letters, how many bits do I need to represent 5 things? 3 bits, right? I mean, it's overkill, but I can't get away with 2, because 2 only represents 4 different things, right? So perhaps this is my fixed length code. A maps to 000, B maps to 001, and so on. Which means if I have 62 bits, 62 letters, how many bits do I need? 186 bits, right? 62 times 3. No data compression yet. Now let's do better. Let's do data compression. Instead of having fixed length, I'm going to use variable length code. I'm going to assign to be 0. B, C, D, E are going to be like this. Well, if you go and count, it'll turn out that instead of 186 bits, now you need 138 bits with no loss. These 138 bits will completely get me back my file. Can anybody see how we got the data compression? Well, we took the symbol that occurred the most. We represented it by a small code word, because, well, here it was represented by 3, but by 3 bits. But if I represent this by 1 bit, then it's going to add only 1 bit 24 times instead of 24 times 3, right? So now the rest I did like this. Now you could ask. Now you notice that for the rest, I had to start that with a 1, because if you start with a 0, you won't know. Like if this was 000, you don't know if this is 3 A's or a B, right? Okay, but anyway, when we talk about source coding, we'll talk about designing codes. We'll talk about that. But my point here is I represented that file per less bits. This is data compression. This is source coding. Okay. Now you might ask, why can't I do this? Why can't I put a 0 then 1 1 1 0 0 1 0 0? Well, we already saw this 0 0. This is not compatible, right? Okay. And here, this first 0, even though there's no 0 1, once I get this 0, I don't know if it's that one or something else. It turns out this code is bad. It's not uniquely decodable. And you can immediately see that from, is a 0 0 equal to E or AA? So it's not, so this is bad. This turns out is good. This is uniquely decodable. Okay? So have I convinced you that you could compress? I mean, this, you could do this for any file, right? I mean, this is naive compression, but it allows me to get across the idea to you, you can do compression. This is why you should use WinZip or PKZip or whatever tool you use for zipping. Okay, this is lossless data compression, and it is right there. Every communication system has it. Why? Why send more than you have to? Right? It costs you money to transmit data. It costs you resources, power, energy. Why send more than you have to? Okay, so all systems use data compression. Okay, let's talk about channel coding. Okay, so we already finished source coding. Okay, let's talk about channel coding. Okay, so channel coding is the idea of getting robustness to errors. Between your transmitter and receiver, you can have a channel that can introduce errors, noise. Okay, so now I want to convince you also that you do channel coding in your everyday life. Tintin. So Tintin, we're on the phone. All right, I'm talking to you. And the line's a bit noisy. Right? Like let's say we're using an operator that doesn't have good coverage, it's a bit bad connection. And I say something to you and you don't hear me. What am I going to do? I'm going to repeat. And I'm going to repeat it until you understand. That's actually redundancy, right? Yeah. So do you already see that adding redundancy gives you robustness to noise? And so we're going to take the idea of repetition and build a code. Okay. What I'm going to do is for every bit that comes in, I'm going to output n bits. So if n is 3, when I want to send a 0, I transmit 0, 0, 0. When I want to transmit a 1, I transmit 1, 1, 1. Now keep in mind that when I say transmit, I'm talking about the output of the channel encoder. Eventually, remember, there's a modulator, right? Because we only transmit analog signals with zeros and ones embedded in there. So please allow me to say I transmit a 1 or transmit a 0. You know what I mean, right? What I mean is that 1 gets embedded into the waveform. But to avoid having to say that over and over again, I'll just say transmit a 0 or transmit a 1. So in channel coding, with the repetition code, when I send, if my repetition factor is 3, when I want to send a 0, I send 3 zeros. When I want to send a 1, I send 3 ones. Now, tell me, how are we going to decode that? Let's say I send you some information and you receive 101. What are you going to decode to? What do you think I sent you? Did I send you a 1 or a 0? You receive the string 101. You know we are using a repetition 3 code. So what did I send you? Did I send you a 1 or a 0? 1. So remember the encoding scheme. When I want to send you a 0, I'll send you 3 zeros. When I send you a 1, I'll send you 3 ones. Obviously, if you receive 3 zeros or 3 ones, so if you receive 3 ones, what did I send you? 1. Yeah? If you receive 3 zeros, what did I send you? 0. If you receive 101, what did I send you? 1. Right? Because there's more ones, right? So you just derived majority voting or majority decoding. And it turns out that's the optimum decoding scheme here. But did you notice you corrected the error? Because 101, the middle bit was an error. When you took the majority vote, you still decoded 201. I'm just giving you an example. We do not use repetition code in practice because it's very inefficient. But it's a way for me to get across the idea that adding redundancy can give us power. One other thing you can decide, when you got a 101, what else do you know? Something else you know. You know there was an error. That's error detection. Now, in this case, you can correct the error. Well, 101, why couldn't it be the case that I actually sent a 0 and 2 bits got flipped? That means error correction is not foolproof. If 1 bit got flipped, you can correct it, right? Again, there's no free lunch. There's no way to get over, to solve all problems, because you actually are not a genie. You don't know what happened in the channel, but the redundancy buys you something. Okay. Now, repetition coding is very bad because for every 3 bits, I'm sending 1 bit of information. So my rate of communication is 1/3. And as now you can see that with the rate 3 code, rate 1/3 code, I can correct 1 error. With the rate 1/5 code, how many errors can I correct? If I repeat 5 times, then if 2 bits get flipped, can I correct them? Yes. Yeah, because it's not more than half. So you can see that if I increase that redundancy, I increase my power. But you're also decreasing your rate of communication. And repetition code, the rate is 1/n. It goes to 0 as n goes to infinity. That's why it's very bad. But it's good for us to explain. But it turns out channel coding, the whole field of channel coding and coding theory, can design codes that give you a positive rate as n goes to infinity. That's why channel coding is so powerful and why Shannon's ideas are so powerful. Okay, we're going to talk about some codes that help you do all this stuff without the rate going off to 0, which means you can actually send some information. If the rate went to 0 and you wanted more and more error correction and error detection, then that's no good, right? It's like saying, I give you a lot of power, but then I take it away by not letting you use it. Okay, but there exist good codes. Shannon proved there exist good codes whose rate doesn't go to 0 that give you error correction and error detection. So are you with me? And down here, yeah. So I was just saying, if n is 5, you can detect 4 errors, right? And you can correct 2. Why can you detect 4 errors? Because if 4 bits flipped, it's not one of the code words, right? The 2 code words are 00000 or 11111. As long as you receive something that's not a code word, it's an error. So you can detect 4 errors and correct 2. And this 2 is because 2 errors doesn't push you past the halfway point. 3 errors pushes you past the halfway point. It's closer to the other one. It's 2 errors away from the other choice. Okay? So it turns out if n is 2m plus 1, you can detect 2m errors and correct m errors. But as I said, repetition coding bad because your rate is 1/n. And 1/n goes to 0 as n goes to infinity. Okay, good. So I think that's all I want to say about these two. I'll say one last thing, which is our friend Shannon. Okay, back to Shannon and 1948. Shannon showed that there exist good coding strategies, and by code we mean the channel codes. Yeah. Okay, there exist good channel codes that can give you arbitrarily low error probability without the rate going to 0. Repetition coding is not the answer. It was my way of explaining channel coding. But Shannon proved it, and that's why his paper was groundbreaking, because it allowed people to search for these codes. He showed under what conditions do they exist. All right? And the whole field of coding theory is this. And, it would take somebody years and years to study all of it. Even I haven't studied it all. For the past 70 years, people have studied. Okay. The other thing that Shannon showed, so I told you that under certain conditions, good code exists. What is that condition? That condition is that given a channel, Shannon defined the capacity of the channel. And it turns out that capacity is the maximum rate of communication, of reliable communication. Yeah, so as long as I give you a channel, he showed you how to compute the capacity, and as long as you operate the system below its capacity, you can operate it perfectly. You see how powerful that idea is, right? And so for an additive white Gaussian noise channel, this is the most popular channel model in engineering. It stands for, so AWGN is additive white Gaussian noise. Noise means that the thing you're adding, the corruption is noise. You don't want it. It's bad, right? It adds to your signal. So the channel model is something like this. The output is the input plus noise. Okay? Right? I receive Y, I want X. Okay? With noise. So the noise is that it's undesired. The additive means it's adding. And I'm going to let you guys figure out what white and Gaussian means. But what Shannon showed is that given an additive white Gaussian noise channel, this is the capacity. And this is, if you study communications, this is very famous. It's like log 1 plus signal to noise ratio. This is what I call the log 1 plus SNR formula. W is the bandwidth, P is the transmit power, and W is the bandwidth, and N0 is the noise power. Okay? And so he showed that this is the capacity, that if you have an additive white Gaussian noise channel, this is the maximum rate of reliable communication. Now, the reason AWGN is important is that the telephone line, a lot of channels are modeled well by AWGN. Okay?